Hello there, and welcome to the Sleepy Science Channel. Tonight, we turn our gaze to one of the most enchanting phenomena in all the heavens, the falling star. These brilliant streaks of light have captivated humanity since the first eyes looked upward into darkness. They are fleeting, mysterious, and impossibly beautiful. Brief flashes that remind us the universe is always in motion, always surprising us with its silent poetry written across the night. If you enjoy these gentle explorations into the cosmos, I invite you to like and subscribe, or leave a thought in the comments below. It helps others find their way here, one peaceful soul at a time. But for now, there is nothing you need to do except settle in, let your breathing slow, and allow the wonder of falling stars to carry you into rest. Let us begin. The ancient wonder of shooting stars. Falling stars are not stars at all, but fragments of space crossing into our world. When we see a streak of light flash across the darkness, we instinctively call it a shooting star or a falling star. Yet despite these names, what we witness is not a star. Stars are distant suns, massive and burning with nuclear fire, anchored in their places across unimaginable distances. What streaks above us is something far more intimate, a fragment of rock or metal, often no larger than a grain of sand, plunging into Earth's atmosphere at tremendous speed. As these tiny travelers slam into the blanket of air surrounding our planet, friction heats them to extraordinary temperatures. They begin to glow, blazing brilliantly against the black canvas of night. Most burn completely away before ever reaching the ground, vaporized by the intensity of their descent. What remains is light, pure, fleeting, beautiful light. A final goodbye from a piece of cosmic debris that has wandered the solar system for millions or even billions of years. The ancient Greeks called them asters planetae, wandering stars. They did not understand what caused them, but they recognized their beauty and their mystery. To see one was considered a moment of connection with the divine, a sign from the gods, or an omen of things to come. Even now, in our age of science and understanding, the sight of a falling star still inspires wonder. We make wishes upon them. We pause our conversations to watch them, and we feel, if only for a moment, that we have witnessed something magical. Every night, somewhere on Earth, falling stars are streaking through the darkness. They arrive continuously, a gentle rain of cosmic dust that never stops. Most go unseen, burning up over oceans or deserts, or during daylight when the sun's brilliance drowns them out. But on a clear night, away from city lights, you might see several in an hour. Each one is a small miracle, a reminder that our planet is constantly moving through a vast ocean of debris, left behind by comets and asteroids. The science behind the glow. Falling stars burn because of speed, not fire. When a meteoroid, as these fragments are properly called, enters Earth's atmosphere, it is traveling at astonishing velocities. Some arrive at 15 kilometers per second. Others move even faster, approaching 70 kilometers per second. At these speeds, the air itself becomes a barrier, a wall of molecules that the meteoroid must push through. But air is not empty. Even at high altitudes where the atmosphere is thin, there are still countless molecules of nitrogen and oxygen. As the meteoroid plows through them, it compresses the air in front of it. This compression generates heat, tremendous heat, enough to raise temperatures to thousands of degrees. The surface of the meteoroid begins to melt and vaporize, creating a glowing plasma trail behind it. This is what we see from the ground, not the meteoroid itself, which is often too small to be visible, but the superheated air around it, glowing like a neon sign in the night. The colors can vary depending on the composition of the meteoroid and the gases in the atmosphere. Most appear white or yellowish, but some flash green from nickel, orange from sodium, or even blue from magnesium. Each streak is unique, a signature of chemistry and velocity written across the sky. The trail itself is called a meteor. If the object survives its fiery descent and reaches the ground, it earns a new name, meteorite. But most never make it that far. They are simply too small, too fragile. They give everything they have in those few seconds of brilliance, lighting up the night before, disappearing into atoms and memories. Scientists estimate that Earth sweeps up about 100 tons of meteoritic material every single day. That sounds like a lot, but spread across the entire surface of the planet, it is vanishingly small. Most of it arrives as dust, microscopic particles that drift down through the atmosphere so gently they never even glow. The ones we see, the ones that blaze across our vision, are the exceptions. They are the fragments large enough and fast enough to announce their arrival with light. Meteors, meteoroids, and meteorites. The naming can seem confusing at first, but there is a simple logic to it. Before it enters Earth's atmosphere, while it is still floating through space, the fragment is called a meteoroid. It might be a fleck of dust, a pebble, or even a boulder. It drifts in silence, invisible, one of countless pieces of debris orbiting the sun. When that meteoroid enters the atmosphere and begins to glow, it becomes a meteor. This is the streak of light we see. The term meteor refers specifically to the phenomenon, the bright trail, not the object itself. It is the event, the moment of burning. If any portion of the original meteoroid survives the journey through the atmosphere and lands on Earth's surface, it is then called a meteorite. These are rare treasures, pieces of space that can be held in your hand. Scientists study them carefully, analyzing their composition to learn about the early solar system. Some meteorites are older than Earth itself, fragments from the time when planets were just beginning to form. But the vast majority of meteors never become meteorites. They are entirely consumed by their descent, transformed from solid matter into light and heat. In a way, this makes them even more poetic. They give up their physical form to create a moment of beauty, a fleeting spectacle that lasts only seconds but can be remembered for a lifetime. Ancient cultures did not have these distinctions, of course. To them, a falling star was simply that, a star that had somehow broken free from the heavens. Some believed they were the souls of the departed, ascending or descending between worlds. Others thought they were messages, signs to be interpreted by priests or shamans. In many traditions, seeing a falling star was considered good luck, a blessing from the cosmos. Even today, the tradition of making a wish on a shooting star persists. There is something deeply human about it, this desire to connect our hopes to something beyond ourselves. When we see that streak of light, we feel, instinctively, that we are witnessing something special, and so we whisper our dreams into the darkness, hoping they might be carried upward on the trail of light left behind. The origins of cosmic debris. Where do these fragments come from? The solar system is not empty space. Between the planets, scattered throughout the vast distances, are countless pieces of rock and metal. Some are asteroids, minor planets that never coalesced into larger worlds. Others are the remnants of comets, icy wanderers that shed dust and debris as they approach the sun. Comets are particularly important sources of meteors. As a comet nears the sun, the heat causes its icy surface to vaporize, releasing gas and dust into space. This material forms the comet's distinctive tail, always pointing away from the sun, pushed by solar wind and radiation pressure. But the tail does not simply vanish. The dust particles remain in orbit, spreading out along the comet's path. Over time, These particles form a broad stream, a river of debris, following the same orbital route as the parent comet. If Earth's orbit happens to intersect this stream, we pass through it like a ship cutting through fog. As we do, thousands upon thousands of these dust grains enter our atmosphere, creating a meteor shower. These are not random events, but predictable encounters that occur at the same time each year as Earth returns to the same point in its orbit. Some meteor showers are associated with comets that still exist, comets we can observe and track. The Perseids, for example, come from comet Swift-Tuttle, which returns to the inner solar system every 133 years. The Leonids originate from comet Tempel-Tuttle, which orbits every 33 years. Even when the comet itself is far away, its dusty legacy remains, waiting for Earth to pass through. Other meteors are more random, not part of any particular shower. These are called sporadic meteors, and they can appear from any direction at any time. They come from the general background of debris that fills the solar system, fragments that have been wandering for so long their origins are uncertain. They might be pieces of asteroids that collided billions of years ago, or dust from comets that no longer exist. Each one carries a history we can only guess at. The atmosphere as a shield. Earth's atmosphere is both destroyer and revealer. Without it, meteoroids would strike the surface constantly, pummeling the ground like raindrops. Our planet would be as cratered as the moon, scarred by endless impacts. But the atmosphere acts as a shield, a protective blanket that burns away most incoming fragments before they can cause any harm. This shield is not uniform. It is a layered structure, each layer with its own characteristics. The lowest layer, the troposphere, is where we live and breathe. Above that is the stratosphere, then the mesosphere, and finally the thermosphere, which extends hundreds of kilometers above the surface. Meteors typically begin to glow in the mesosphere, at altitudes between 80 and 120 kilometers. At these heights, the air is incredibly thin, but still dense enough to create friction. The meteoroid, moving at hypersonic speeds, encounters resistance. The air cannot move out of the way fast enough, so it compresses, heats, and begins to strip material from the meteoroid's surface. This process is called ablation, and it is what creates the glowing trail. From the meteoroid's perspective, if such a thing could have a perspective, the experience would be violent and brief. In less than a second, it transitions from the cold vacuum of space to an environment where it is being torn apart by forces beyond comprehension. The surface melts, vaporizes, and is blown away. Smaller fragments break off and burn separately. Within moments, nothing remains but a dispersing cloud of atoms and a fading streak of light. From our perspective on the ground, the experience is entirely different. We see only beauty, a silent flash, a graceful arc, a moment of light in the darkness. We do not hear the meteor because sound travels slowly, and most meteors occur far above where sound can reach us effectively. We do not feel any impact or disturbance. We simply witness light, and then it is gone. This transformation, from violent destruction to peaceful beauty, is part of what makes falling stars so captivating. They remind us that the universe operates on scales we can barely imagine, where forces that would annihilate us manifest as gentle streaks across the night. They are both terrifying and tender, a paradox written in light, colors in the darkness. Not all meteors shine the same way. If you watch carefully during a meteor shower, you might notice variations in color and brightness. Some flash brilliant white, others glow yellow or orange, and occasionally one will streak across in vivid green or even blue. These colors are not random. They reveal the composition of the meteoroid and the chemistry of its destruction. White and yellow meteors are the most common. These colors come from the intense heat and the presence of iron and other common elements. Most meteoroids contain iron, so most meteors exhibit these warmer tones. The glow is similar to heated metal in a forge, shifting from red to orange to yellow to white as temperatures increase. Green meteors are particularly striking, and they indicate the presence of nickel or copper. When these elements vaporize in the heat of entry, they emit light at specific wavelengths that our eyes perceive as green. A bright green meteor can seem almost magical, a streak of emerald fire that feels out of place among the usual warm tones. Blue and violet meteors are rarer still. They suggest the presence of magnesium or calcium. These cooler colors stand out dramatically against the black sky, creating an impression of something otherworldly. Some observers describe blue meteors as looking like electric sparks, cold and sharp compared to the warm glow of more typical meteors. Orange and red meteors often come from the presence of sodium or ionized atmospheric nitrogen. The exact shade can vary depending on the speed and altitude of the meteor. Slower meteors, or those that penetrate deeper into the atmosphere, sometimes exhibit reddish hues as they interact with denser air. The brightness of a meteor depends on several factors: size, speed, composition, and the angle of entry. A small grain of sand entering at moderate speed might produce only a faint streak, barely visible. A larger pebble arriving at high velocity can create a dazzling flash that lights up the landscape and casts shadows. These brighter meteors are sometimes called fireballs, and they are unforgettable when witnessed. Occasionally, a fireball will be bright enough to rival the full moon or even the sun. These extraordinary events are called bolides, and they can produce sonic booms, fragments that reach the ground, and trails that linger in the sky for minutes. Bolides are rare, but when they occur, they become the stuff of legend. Ancient records are filled with accounts of fiery objects crossing the heavens, and many of these descriptions almost certainly refer to bolides. The speed of falling stars. Speed is everything in the life of a meteor. The faster the meteoroid travels, the more energy it carries, and the more dramatic its destruction. The slowest meteors, relatively speaking, enter Earth's atmosphere at about 11 kilometers per second. This is roughly Earth's escape velocity, the minimum speed needed to leave our planet's gravitational influence. Meteoroids arriving at this speed are often associated with asteroid debris, chunks of rock that share similar orbits with Earth. Faster meteors, those arriving at 40 or 50 or even 70 kilometers per second, are typically associated with comets. Comets often have highly elliptical orbits that bring them swooping in from the outer solar system. When their debris streams intersect Earth's orbit, the relative velocities can be enormous. These high-speed encounters produce the brightest and most energetic meteors. To put these speeds in perspective, consider that a bullet from a high-powered rifle travels at about 1 kilometer per second. A meteor moving at 70 kilometers per second is traveling 70 times faster. At such velocities, even a tiny grain of sand carries tremendous kinetic energy. When that energy is converted to heat through friction, the result is a brilliant flash of light. The duration of a meteor's visibility depends on several factors, but speed is one of the most important. Faster meteors burn brighter, but also burn out more quickly. They tear through the atmosphere so rapidly that their moment of glory lasts only a fraction of a second. Slower meteors can glow for several seconds, giving observers more time to follow their path across the sky. The angle of entry also matters. A meteoroid arriving perpendicular to Earth's surface plunges straight down through the atmosphere, experiencing maximum friction and burning up quickly. But if a meteoroid enters at a shallow angle, grazing the upper atmosphere, it can skip along like a stone on water. These grazing meteors can travel across huge distances, sometimes remaining visible for many seconds as they arc across the sky before either burning up or escaping back into space. There are even rare cases of meteors that enter the atmosphere, slow down enough to stop glowing, and then fall the rest of the way to the ground without further light. These are called dark flight meteorites, and they are difficult to find because there is no bright trail to mark where they land. They simply arrive, silent and unnoticed, adding to Earth's mass one small piece at a time. Meteor showers, celestial celebrations. Meteor showers are among the most anticipated events in the astronomical calendar. Unlike sporadic meteors, which can appear at any time from any direction, shower meteors arrive in abundance, sometimes dozens or even hundreds per hour. They seem to radiate from a specific point in the sky, creating a celestial display that can last for hours or even days. The radiant, as this point is called, is not where the meteors actually originate. It is an effect of perspective. Imagine standing on a railroad track and looking down the rails toward the horizon. The parallel tracks seem to converge at a distant point. Meteor shower. Meteors behave similarly. They are actually moving in parallel paths, but because of perspective, they appear to fan out from a single location. The radiant gives each meteor shower its name. The Perseids appear to radiate from the constellation Perseus, the Geminids from Gemini, the Orionids from Orion. These associations make it easier to locate and identify showers, and they connect the celestial events to the ancient star patterns that have guided humanity for millennia. Meteor showers occur when Earth passes through a debris stream left behind by a comet or, less commonly, an asteroid. As our planet moves through this river of dust and pebbles, countless particles enter the atmosphere, creating the shower. The intensity of the shower depends on how dense the debris stream is and how directly Earth passes through it. Some showers are reliable, producing similar numbers of meteors year after year. Others are more variable, with outbursts occurring during certain years when Earth happens to pass through a particularly dense clump of material. Predicting these outbursts is challenging, but astronomers use computer models to calculate the distribution of debris along a comet's orbit, trying to forecast when Earth might encounter richer regions. The best meteor showers occur when several favorable conditions align. The moon should be absent or setting early, leaving the sky dark. The radiant should be high in the sky, which usually means observing after midnight when Earth's rotation has carried your location into a favorable position. The weather should be clear, with no clouds to block the view, and you should be far from city lights, in a location where the sky is truly dark. Under perfect conditions, major showers like the Perseids or Geminids can produce 100 or more meteors per hour. That is nearly 2 every minute, a continuous parade of falling stars. Watching such a display is meditative and humbling. You lie back, gaze upward, and simply receive. The universe puts on a show, asking nothing in return except your attention. The Perseids, summer's gift. The Perseid meteor shower is perhaps the most famous and beloved of all annual showers. It occurs every August, peaking around the 12th or 13th of the month, when Earth passes through the debris stream of Comet Swift-Tuttle. For observers in the northern hemisphere, the Perseids arrive during warm summer nights, making them accessible and comfortable to watch. The Perseids are known for their high rates, often producing 60 to 100 meteors per hour at peak. They are also known for their fireballs, bright meteors that leave persistent trails. These luminous streaks can glow for several seconds after the meteor itself has vanished, twisting and curling as high-altitude winds reshape them. Comet Swift-Tuttle is a large comet, about 26 kilometers across, with an orbital period of 133 years. It last passed through the inner solar system in 1992 and will return again around 2026. Even when the comet is far away, its debris stream remains, a river of dust that Earth crosses every August. The name Perseid comes from the constellation Perseus, which contains the radiant point. Perseus is a northern constellation, visible from most populated areas of Earth. It rises in the northeast after sunset during August and climbs higher as the night progresses. By the early morning hours, it is well placed for meteor observing. Ancient Chinese astronomers recorded the Perseids as early as the 1st century. They called them fire, rain, and noted their regularity. European observers documented them throughout the Middle Ages, often attributing religious significance to their appearance around the feast day of St. Lawrence, which falls on August 10th. The association was so strong that in some regions, the Perseids were called the Tears of St. Lawrence. Modern astronomy has stripped away the omens and the saints, but the wonder remains. To lie on a blanket on an August night, watching the Perseids streak overhead, is to participate in a tradition that spans cultures and centuries. The meteors that burn tonight are siblings to those that amazed observers 1,000 years ago, particles from the same comet, traveling the same ancient path, the Geminids. December's surprise. The Geminid meteor shower is unusual in almost every way. Unlike most major showers, which originate from comets, the Geminids come from an asteroid, or rather, from an object that behaves like an asteroid but might once have been a comet. This parent body, called Phaethon, is a rocky object about 5 kilometers across that orbits the Sun every 1.4 years. Phaethon's orbit brings it very close to the Sun, closer than any other named asteroid. At perihelion, it passes within just 21 million kilometers of our star, well inside the orbit of Mercury. The intense heat at this distance may cause the surface to crack and shed dust, creating the debris stream that Earth encounters every December. The Geminids are arguably the best meteor shower of the year, often surpassing even the Perseids in numbers. At peak, which occurs around December 13th or 14th, observers can see 120 or more meteors per hour under ideal conditions. The meteors are bright, colorful, and moderately fast, making them easy to spot even for casual observers. The radiant lies in the constellation Gemini, which rises in the east during early evening in December. This means the Geminids can be observed from late evening onward, unlike many showers that require waiting until after midnight. For observers willing to brave cold winter nights, the Geminids offer spectacular rewards. What makes the Geminids particularly interesting is their origin story. Most meteor showers have been known for centuries, their parent comets identified long ago. But the Geminids were first recognized as a distinct shower only in the mid-1800s, and their connection to Phaethon was not established until 1983, when the asteroid was discovered. Phaethon itself remains mysterious. Is it an asteroid that happens to shed dust? Or is it a dead comet, its ice exhausted, now behaving like a rocky body? Some astronomers suspect it might be a piece of a larger object that broke apart in the past. Whatever its true nature, Phaethon continues to supply Earth with a reliable annual shower, one that brightens the darkest nights of winter. The Leonids, the storm makers. The Leonid meteor shower has a reputation for extremes. Most years, it produces only modest numbers, perhaps 10 to 15 meteors per hour. But approximately every 33 years, the Leonids explode into a meteor storm, a rare and breathtaking event where thousands of meteors per hour can streak across the sky. These storms occur when Earth passes through a particularly dense clump of debris from Comet Tempel-Tuttle. The comet orbits the Sun every 33 years, and each time it passes through the inner solar system, it leaves behind a fresh trail of dust. When Earth encounters these dense, recently deposited streams, the result is spectacular. The most recent Leonid storm occurred in 1999, when observers in some locations reported seeing thousands of meteors per hour at peak. The sky appeared to be raining fire, with meteors flashing in every direction. Some were bright enough to cast shadows. Others left glowing trains that lingered for minutes. The display was so intense that some observers described feeling disoriented, as if the ground itself were moving. Historical records document Leonid storms going back more than 1,000 years. Chinese astronomers in the year 902 recorded stars falling like rain. In 1833, a spectacular Leonid storm terrified observers across North America. One witness described the sky as appearing to be in flames, with meteors falling so thickly they could not be counted. That 1833 storm was pivotal in the history of meteor science. It prompted researchers to study meteors more systematically and led to the realization that showers were recurring events associated with Earth's orbit. Before this, meteors were seen as random phenomena, impossible to predict or understand. The Leonids proved otherwise. The radiant for the Leonids lies in the constellation Leo, which rises after midnight in November. The shower is active from around November 6th through November 30th, with peak activity around November 17th or 18th. The meteors are fast, entering Earth's atmosphere at 71 kilometers per second, and they often produce colorful fireballs. The Quadrantids, a mystery in January. The Quadrantid meteor shower is both impressive and mysterious. It produces high rates, sometimes rivaling the Perseids or Geminids, but it is far less well known. Part of the reason is its timing. The Quadrantids peak in early January, when weather in the northern hemisphere is often cold and cloudy. Many potential observers are discouraged by the conditions and miss the show. But timing is also an issue in another sense. The Quadrantid peak is sharp, lasting only a few hours. Unlike the Perseids, which maintain high rates for a day or two, the Quadrantids surge to maximum and then decline rapidly. If the peak occurs during daylight or during cloudy weather, an entire year's opportunity can be lost. The radiant lies in what was once the constellation Quadrans Muralis, a star pattern created in the 1700s but later removed from official star charts. The name persists in the shower's title, even though the constellation itself no longer exists. Today, the radiant is located in the northern part of Boötis, near the handle of the Big Dipper. The parent body of the Quadrantids was identified only recently. It is an asteroid called 2003 EH1, a rocky object that might be the remnant of a comet that broke apart centuries ago. Some researchers believe it could be connected to Comet C 1490 Q1, which was observed in the late 1400s and then vanished. The Quadrantids produce bright meteors with a distinctive blue tint, different from the warmer colors of many other showers. They are also known for their fireballs, which can be truly spectacular. For observers willing to brave the cold and wait for the brief peak window, the Quadrantids offer one of the finest displays of the year, the Lyrids, oldest known shower. The Lyrids hold the distinction of being the oldest meteor shower with continuous historical records. Chinese astronomers documented them as early as 687 years before the Common Era, and they have been observed regularly ever since. For more than 2,700 years, humans have watched these meteors streak across April skies. The Lyrids are associated with Comet C, Thatcher, a long-period comet with an orbital period of about 415 years. It last passed through the inner solar system in 1861 and will not return until the 2200s. Yet even in its absence, the dust it left behind continues to create the annual Lyrid shower. The shower is active from about mid-April through late April, with peak typically occurring around April 22nd. Rates are moderate, usually around 10 to 20 meteors per hour, though occasional outbursts can push numbers higher. The meteors are moderately fast and often leave persistent trains. The radiant lies near the bright star Vega in the constellation Lyra. Vega is one of the most brilliant stars in the northern sky, making the radiant easy to locate. The constellation Lyra represents a lyre, the harp of Orpheus in Greek mythology, and there is something poetic about meteors radiating from the instrument of the legendary musician. The Lyrids mark the beginning of spring meteor observing in the northern hemisphere. After the long winter, when only the Quadrantids break the darkness, the arrival of the Lyrids signals that warmer nights are coming. They are a herald of the meteor-rich months ahead, a promise that the sky will soon be filled with falling stars. The Eta Aquarids and Orionids, Halley's children, two meteor showers, occurring 6 months apart, share a common parent. Both the Eta Aquarids in May and the Orionids in October originate from debris left by Halley's comet, the most famous comet in history. As Halley orbits the Sun every 76 years, it sheds material continuously, creating two distinct streams that Earth encounters at different points in our orbit. The Eta Aquarids peak around May 5th or 6th, producing about 30 to 40 meteors per hour for observers in the southern hemisphere and somewhat fewer in the northern hemisphere. The radiant lies near the star Eta Aquarii in the constellation Aquarius, which rises in the pre-dawn hours during early May. The Orionids peak around October 21st, with similar rates. Their radiant is in the constellation Orion, near the raised arm of the celestial hunter. Orion is one of the most recognizable constellations, visible from virtually everywhere on Earth, making the Orionids accessible to observers worldwide. Both showers produce fast meteors, moving at 66 kilometers per second. This high speed often results in persistent trains and bright fireballs. The meteors can appear anywhere in the sky, but if you trace their paths backward, they all seem to originate from the radiant. Halley's comet has been observed for more than 2,000 years, with records going back to ancient China, Babylon, and Greece. It has witnessed empires rise and fall, seen civilizations bloom and fade. The particles burning up as Eta Aquarids and Orionids tonight were shed by that comet on one of its many passes through the inner solar system, perhaps centuries ago. To watch these meteors is to see Halley's legacy written in light. The comet itself will return in 2061, but even now, even decades before that return, it continues to gift us with shooting stars twice a year, a recurring reminder of its existence. Sporadic meteors, the wanderers. Not all meteors belong to showers. Between the predictable annual displays, there is a constant background of sporadic meteors, random fragments that arrive from all directions at all times. On any clear night, even with no shower active, a patient observer can expect to see 5 to 10 sporadic meteors per hour. These wanderers come from the general population of debris that fills the solar system. Some are pieces of asteroids that collided long ago. Others are ancient comet dust from streams so dispersed and scattered that they no longer produce recognizable showers. Still others are fragments from events we can only guess at, cosmic collisions and disruptions that occurred millions of years ago. Sporadic meteors are unpredictable. They can appear anywhere in the sky at any time. They might be faint or brilliant, fast or slow, colorful or white. Each one is unique, carrying its own history, its own chemical signature, Watching for them requires patience and a willingness to simply sit with the night, letting your eyes adjust, waiting for the next flash. There is something meditative about observing sporadic meteors. Unlike a shower, where you can anticipate activity from a specific region, sporadics demand that you remain open, attentive to the entire sky. You cannot predict where the next one will appear. You can only wait and watch and be present. In a way, sporadic meteors are more mysterious than shower meteors. Shower meteors have known parents, identified comets or asteroids. Their paths are mapped, their origins understood. But sporadics are orphans, fragments without clear lineage. They remind us that the solar system is full of unknowns, that not everything can be traced and catalogued and explained. Fireballs, the bright ones. Occasionally, a meteor blazes across the sky with such intensity that it demands attention. These are fireballs, officially defined as meteors brighter than the planet Venus. But the term is used more broadly to describe any meteor that is strikingly brilliant, bright enough to cast shadows, illuminate the landscape, or cause people to stop and stare. Fireballs can occur during showers or as sporadic events. They are caused by larger fragments, objects that might be the size of a pebble, a fist, or even larger. As these meteoroids plow through the atmosphere, they carry more mass and more energy, creating correspondingly brighter displays. Some fireballs are white or yellow, blazing like miniature suns. Others flash green or blue, their colors revealing unusual compositions. A few exhibit multiple colors as they fragment, breaking apart in mid-flight and scattering pieces that burn at different temperatures and compositions. The brightest fireballs can be truly spectacular. They can light up the night, like daylight, for an instant, turning the landscape into stark relief. Trees cast shadows, faces are illuminated, and the entire world freezes in a moment of silent brilliance. Then it is gone, and the darkness returns, deeper than before. Witnesses to major fireballs often describe feeling disoriented or startled. The sudden flood of light triggers instinctive reactions, a brief surge of adrenaline, a sense that something significant has just occurred. And in a sense, it has. Fireballs are rare enough that most people see only a handful in their lifetimes. To witness one is to see something genuinely extraordinary. Some fireballs leave persistent trains, glowing trails that linger in the sky long after the meteor itself has burned away. These trains are composed of ionized gas, atoms that were stripped of electrons during the meteor's passage. As these ions recombine with electrons, they emit light, creating a ghostly afterimage that can last for minutes. High-altitude winds twist and distort these trains, turning them into serpentine shapes that drift and curl. Watching a train evolve is like watching a slow-motion painting being created in the sky. What begins as a straight line becomes a curve, then a spiral, then a dissipating cloud. It is art created by physics, beauty born from destruction. Bolides, the thunderous ones. A bolide is a fireball taken to the extreme. Not only is it exceptionally bright, but it also produces a sonic boom, a thunderous sound that can rattle windows and startle people across a wide area. Bolides occur when particularly large meteoroids, perhaps meters across, penetrate deep into the atmosphere before exploding or fragmenting. The sound of a bolide can arrive minutes after the visual display, because light travels much faster than sound. Witnesses often describe seeing a brilliant flash, then waiting in silence, wondering if they imagined it. Then the boom arrives, a deep rumble or sharp crack that confirms the event was real. Some bolides explode at high altitude, fragmenting into dozens or hundreds of smaller pieces. These airbursts released tremendous energy, enough to shake buildings and trigger earthquake sensors. The Chelyabinsk meteor in 2013 was a bolide that exploded over Russia, releasing energy equivalent to hundreds of thousands of tons of explosives. Its shockwave broke windows across 6 cities and injured more than 1,000 people, mostly from flying glass. Despite the drama, bolides rarely cause direct harm. The atmosphere absorbs most of the energy, and fragments that survive to reach the ground are usually small and scattered. But the psychological impact can be significant. The sudden noise, the shaking, the blast of light, all trigger primal fears. Ancient observers would have interpreted such events as divine wrath or omens of disaster. Today, we understand that bolides are simply larger meteoroids, following the same physics as their smaller cousins. They arrive more rarely because large objects are less common than small ones, but they follow the same patterns, the same laws. They are not omens, but they remain impressive, reminders of the energies involved when objects moving at cosmic speeds encounter our atmosphere. Meteorites, gifts from space. Most meteors burn completely away, but a few survive. If a fragment reaches the ground, it becomes a meteorite, a tangible piece of space that can be held, studied, and preserved. Meteorites are rare treasures, windows into the history of the solar system, and they have captivated humanity for millennia. Ancient cultures revered meteorites as sacred objects. Some were incorporated into religious artifacts or monuments. The Kaaba in Mecca contains a black stone that many believe is a meteorite. Native American tribes crafted tools and weapons from meteoric iron long before they developed iron smelting. To these cultures, meteorites were gifts from the sky, materials sent by gods or spirits. Modern science has revealed that meteorites are indeed gifts, but from the solar system rather than deities. They are fragments of asteroids, remnants from the time when planets were forming. Most are older than Earth itself, dating back more than 4.5 billion years. To hold a meteorite is to touch the primordial material that built our world. There are 3 main types of meteorites, classified by composition. Stony meteorites, the most common, are made primarily of silicate minerals. They resemble terrestrial rocks, but often contain small spherical inclusions called chondrules, tiny droplets of once molten rock. Iron meteorites are made of iron-nickel alloys and are much denser and heavier than normal rocks. Stony iron meteorites are mixtures, containing both silicate minerals and metal, and they are the rarest type. Each type tells a different story. Stony meteorites come from the outer layers of asteroids, material that never melted or differentiated. Iron meteorites come from the cores of larger asteroids that did melt and separate into layers just like Earth. Stony iron meteorites come from the boundary regions between core and mantle, rare glimpses into the interiors of shattered worlds. Finding a meteorite is difficult. They look similar to many terrestrial rocks, especially if they have been weathered, but there are clues. Meteorites often have a dark, glassy crust, called a fusion crust, formed when the surface melted during entry. They are often denser than terrestrial rocks, especially if they contain metal, and they are often magnetic due to their iron content. Famous falls. Throughout history, certain meteorite falls have captured public attention, becoming famous events that are remembered and studied for decades. The Allende meteorite, which fell in Mexico in 1969, is one of the most studied meteorites ever recovered. It is a carbonaceous chondrite, a type that contains organic compounds and water-bearing minerals. Scientists believe such meteorites may have delivered the building blocks of life to early Earth. The Murchison meteorite, which fell in Australia in the same year, is similarly important. Analysis revealed it contains amino acids, the building blocks of proteins, proving that organic chemistry occurs naturally in space. These molecules were not produced by life, but they are the same molecules that life uses, suggesting that the ingredients for life are common throughout the cosmos. The Hoba meteorite in Namibia is the largest known meteorite, weighing about 60 tons. It has never been moved from where it fell, remaining in place as a tourist attraction. Its size suggests it must have slowed significantly during entry, likely fragmenting and shedding mass before impact. Otherwise, it would have created a large crater. The Chelyabinsk meteorite, from the 2013 Bolide, was extensively studied because its arrival was captured by numerous dashboard cameras and security cameras throughout the region. This unprecedented documentation allowed scientists to reconstruct the meteor's trajectory, speed, and behavior in extraordinary detail. Fragments recovered from the impact site provided physical samples to correlate with the visual data. Some falls are witnessed by hundreds or thousands of people, while others land in remote areas and are discovered only later, sometimes years or decades afterward. The Willamette meteorite in Oregon was found by Native Americans and held sacred for generations before being moved to a museum. Its deeply pitted surface, eroded by water over centuries, gives it an otherworldly appearance. Meteor craters, scars in stone. When a very large meteoroid survives the atmosphere and strikes the ground with significant speed, it creates an impact crater. These craters are rare on Earth compared to other worlds, because our planet is geologically active and has weather and erosion that gradually erase scars. But some craters remain, silent testaments to ancient impacts. Meteor crater in Arizona is one of the best preserved impact craters on Earth. It is about 1.2 kilometers across and 170 meters deep, created about 50,000 years ago when an iron meteoroid, roughly 50 meters across, struck the desert. The impact released energy equivalent to several megatons of explosives, devastating the surrounding landscape. The Chicxulub crater, buried beneath the Yucatan Peninsula in Mexico, is much larger and more famous. It is about 180 kilometers across and was created 66 million years ago when an asteroid, perhaps 10 kilometers wide, struck Earth. This impact is widely believed to have triggered the mass extinction that ended the age of dinosaurs, throwing up dust and debris that blocked sunlight and collapsed ecosystems worldwide. Impact craters are not just scars. They are also windows into Earth's past, preserving evidence of events that shaped the planet's history and its evolution of life. The Vredefort crater in South Africa, more than 2 billion years old and 300 kilometers across, is the largest confirmed impact structure on Earth. It formed when Earth was young, and its rocks tell stories of a time almost unimaginably ancient. Studying impact craters helps scientists understand the frequency and scale of impacts throughout history. By counting craters on the Moon and other worlds where they are better preserved, researchers can estimate how often impacts of various sizes occur. This data is crucial for assessing the ongoing risk of future impacts and for understanding how impacts have influenced Earth's biological and geological history. Meteorite hunting. Finding meteorites has become a hobby and even a profession for some. Meteorite hunters travel to places where meteorites are easier to find, places where dark rocks stand out against light backgrounds, and where erosion and weathering are slow. Antarctica is ideal because meteorites lie on ice, clearly visible, and the cold, dry conditions preserve them well. Deserts are also popular hunting grounds for similar reasons. When a meteorite is found, its location and context are carefully documented. Scientists want to know where it fell, how long it has been there, and what conditions it has been exposed to. This information helps them interpret the meteorite's properties and chemistry. Even a small meteorite can provide valuable data if properly studied. Some meteorites are more valuable than others, both scientifically and commercially. Rare types, such as lunar or Martian meteorites, command high prices. Yes, we have meteorites from the Moon and Mars. They were blasted off those worlds by ancient impacts and eventually fell to Earth. Holding a piece of Mars, a fragment from another planet, is an extraordinary experience, a tangible connection to worlds we have only begun to explore. The study of meteorites has revolutionized our understanding of the solar system. Before space probes, before samples returned from the Moon, meteorites were our only physical samples from beyond Earth. They still provide unique information, representing a wider variety of bodies than we have visited. Meteorites come from asteroids throughout the asteroid belt, from the Moon, from Mars, and perhaps from comets, offering a cosmic sampling that no mission could match. The history of meteor science. For most of history, meteors were mysterious and frightening. Ancient philosophers debated their nature. Aristotle believed they were atmospheric phenomena, exhalations from Earth, ignited by celestial fire. This view persisted for centuries, relegating meteors to the realm of weather rather than astronomy. The idea that rocks could fall from the sky was dismissed as superstition by many Enlightenment thinkers. In 1790, the French Academy of Sciences declared that meteorites did not exist, that reports of stones falling from the heavens were the result of ignorance or deception. Witnesses were not believed. Samples were ignored. This skepticism began to crumble in the early 1800s. In 1803, a well-documented fall in L'Aigle, France, produced thousands of stones witnessed by numerous reliable observers. A young scientist named Jean-Baptiste Biot investigated and concluded that the stones were indeed extraterrestrial. His report convinced the scientific community that meteorites were real. The 1833 Leonid storm further demonstrated that meteors were astronomical phenomena, not atmospheric. Observers realized that meteors arrived from space, not from within Earth's air. The study of meteors began in earnest, with careful observations, trajectory measurements, and chemical analyses. By the late 1800s, astronomers had connected meteor showers to comets, tracing the Perseids to comet Swift-Tuttle and the Leonids to comet Tempel-Tuttle. This established that at least some meteors were cosmic debris, material shed by comets as they orbited the Sun. The realization transformed meteors from omens or curiosities into keys for understanding the solar system. Throughout the 20th century, meteor science advanced rapidly. Radar allowed meteors to be detected during daylight and through clouds. Photography enabled precise trajectory measurements. Chemical analysis revealed meteorite compositions. And eventually, spacecraft missions to comets and asteroids provided context, showing us the parent bodies from which meteors originate. Today, meteor science is a mature field, combining observation, laboratory analysis, and computer modeling. Researchers track meteor showers, predict outbursts, study meteorite compositions, and assess impact risks. Meteors have gone from feared omens to understood phenomena, but they have lost none of their beauty or their ability to inspire wonder. Cultural meanings across time. Falling stars have meant different things to different cultures throughout history. To the ancient Greeks, they were signs from the gods, messages encoded in light. A bright meteor might herald the birth of a hero or warn of impending disaster. The philosopher Ptolemy suggested that when gods looked down at Earth, gaps opened in the celestial sphere, allowing heavenly fire to fall through. Chinese astronomers kept meticulous records of meteors for thousands of years. They categorized them by color, brightness, direction, and date. believing they reflected the state of the empire and the will of heaven. A meteor falling toward the east might predict conflict in that direction. One that fragmented could symbolize the division of a kingdom. In Islamic tradition, meteors were thought to be weapons hurled by angels at demons attempting to eavesdrop on divine counsels. This belief is referenced in the Quran, where shooting stars drive away those who would steal celestial secrets. The meteors were protectors, guardians of the boundary between heaven and earth. Many Native American tribes saw meteors as spirits traveling between worlds. Some believed they were the souls of the recently deceased, ascending to the afterlife. Others thought they were messengers bringing visions or guidance to shamans and elders. Meteor showers were times of heightened spiritual activity, when the veil between worlds grew thin. European folklore often cast meteors as omens, usually negative. A falling star might predict death, war, or famine. In some traditions, each person had a star, and when it fell, that person died. This belief gave meteors a personal significance, connecting individual fates to cosmic events. But not all traditions viewed meteors darkly. In many cultures, they were seen as good luck. To see a falling star was a blessing, an opportunity to make a wish. This tradition persists today, one of the few pieces of meteor folklore that has survived into modern times. The origins of wish-making on falling stars are unclear, but the practice is nearly universal. In Japan, meteors were called shooting stars or falling stars, much like in English, but they were also associated with the temporary nature of beauty and life. The sudden appearance and disappearance of a meteor reflected Buddhist teachings about impermanence. To see one was a reminder to cherish the present moment. Australian Aboriginal peoples incorporated meteors into their Dreamtime stories. Some saw them as campfires of ancestors crossing the sky. Others believed they were spirits hunting or traveling. The integration of meteors into creation myths shows how deeply these celestial events were woven into cultural understanding of the cosmos. Wishes upon falling stars. The tradition of making wishes on falling stars is ancient and widespread, though its exact origins are lost to time. Some trace it to Ptolemy's writings, where he suggested that gods occasionally peered down at Earth, and during these moments, prayers might be more likely to reach them. A falling star, then, was a sign that the gods were watching, an opportune moment to make a wish. Others connect it to the belief that each person has a star, and when it falls, it represents that person's soul or fate in motion. To make a wish at such a moment is to influence one's destiny, to guide the falling star toward a desired outcome. Whatever its origins, the tradition has persisted across centuries and cultures. Even in our scientific age, when we know that meteors are not stars but grains of dust, the impulse to wish remains. There is something about the sudden, unexpected beauty of a falling star that invites participation. We want to be part of the moment, to give it meaning beyond mere physics. The rules vary by culture and family tradition. Some say you must make your wish before the meteor disappears. Others say you must keep the wish secret, or it won't come true. Some believe the first person to see the meteor gets the wish, while others think everyone who sees it can make one. Psychologically, the act of wishing serves a purpose. It forces us to articulate what we want, to bring our hopes into conscious awareness. The meteor becomes a trigger, a prompt to think about our desires and dreams. Whether the wish comes true is beside the point. The value lies in the wishing itself, in the moment of hope and intention. In a way, meteors are perfect vessels for wishes. They are brief and beautiful, appearing without warning and vanishing just as quickly. They cross the entire sky in seconds, traveling from horizon to horizon, as if carrying our wishes with them. They burn brightly before fading, just as our hopes burn bright before reality tempers them. And there is something generous about the universe offering these moments. Meteors are free, democratic. They appear to rich and poor alike, to the learned and the ignorant. Anyone can see one. Anyone can wish. The cosmos does not discriminate in its gift of falling stars. Meteor photography. Capturing meteors on camera is a challenge that combines skill, patience, and luck. Unlike stars or planets, which remain visible for long periods, meteors are fleeting. They appear and vanish in seconds, giving photographers little time to react. And yet, the results can be stunning, freezing moments of cosmic beauty that would otherwise exist only in memory. The traditional approach to meteor photography involves long exposures. A camera is mounted on a tripod, pointed at a dark region of sky, and left to expose for many seconds or even minutes. If a meteor happens to pass through the frame during the exposure, it will leave a bright streak on the image. The longer the exposure, the more chance of capturing something, but also the more the stars will trail due to Earth's rotation. Modern digital cameras have made meteor photography more accessible. High-sensitivity sensors can capture faint meteors that film would miss. Wide-angle lenses cover large portions of sky, increasing the odds of catching a meteor. And time-lapse sequences, where hundreds of short exposures are taken over hours, can later be reviewed to find any meteors that appeared. During major meteor showers, photographers often set up multiple cameras, all pointed at different regions of sky, all capturing images continuously throughout the night. Later, they sort through hundreds or thousands of images, looking for those few precious frames that contain meteors. It is labor-intensive, but the rewards can be extraordinary. Some meteor photographs capture fireballs, brilliant streaks that dominate the image. Others show persistent trains, glowing trails that linger behind the meteor. A few lucky photographers have captured meteors fragmenting, breaking apart into multiple pieces that create complex, branching trails. Combining multiple meteor images into a single composite can create striking artistic effects. A photograph showing dozens of meteors radiating from a single point illustrates the shower's radiant beautifully. Such images are often more illustrations than pure documents, but they communicate the experience of watching a shower in a way that single frames cannot. The rise of all-sky cameras and meteor detection networks has added a scientific dimension to meteor photography. These systems automatically record the entire sky continuously, capturing every meteor that appears. The data helps researchers track showers, identify new ones, and study the flux of meteors entering Earth's atmosphere. What began as artistic pursuit has become valuable science. Meteor sounds, the mysterious hiss. For centuries, observers have reported hearing sounds associated with meteors, particularly bright fireballs. These reports were often dismissed as impossible. Sound travels much more slowly than light, and meteors occur at altitudes of 80 kilometers or more. The sound of a meteor should not reach the ground until minutes after the visual display, not simultaneously. Yet the reports persisted. Witnesses described hissing, crackling, or popping sounds that occurred at the same moment they saw a bright meteor. The experiences were consistent across cultures and time periods, suggesting they were not simply fabrications. But how could sound arrive instantly when physics said it should not? The mystery was solved, partially, in the late 20th century. Researchers proposed that very bright meteors generate electromagnetic fields that can induce currents in nearby objects. These currents, in turn, can produce audible sounds. The mechanism is similar to how radio waves can make certain materials buzz or click. The sounds are not coming from the meteor itself, but from objects on the ground responding to the meteor's electromagnetic emissions. This explanation accounts for the simultaneous nature of the sounds. Electromagnetic waves travel at the speed of light, so they arrive at the same instant as the visual display. The sounds are generated locally, by objects near the observer, not by the distant meteor. This is why the sounds are often described as coming from nearby trees, grass, or even the observer's own clothing. Not everyone hears these sounds, and they are most commonly reported during very bright fireballs. The phenomenon remains somewhat mysterious, with ongoing research into the exact mechanisms involved. But the experiences of observers are no longer dismissed. The sounds are real, even if unusual. The traditional sonic booms from bolides remain, of course. These are pressure waves created when a large meteoroid passes through the atmosphere faster than the speed of sound. The booms arrive minutes after the visual display, consistent with the time it takes sound to travel from the meteor's altitude to the ground. These sounds are loud, unmistakable, and sometimes powerful enough to shake buildings. The Taurid complex, a hidden danger. Most meteor showers pose no danger to Earth. The particles are tiny, burning up harmlessly in the upper atmosphere. But one stream deserves special attention. The Taurid complex is a broad, diffuse stream of debris that Earth encounters twice a year, in late June and again in November. Unlike most streams, which are dominated by dust, the Taurids contain larger objects, including boulders and possibly even small asteroids. The parent body of the Taurids is Comet Encke, a short-period comet with an orbital period of just over 3 years. But Encke is likely a fragment of a much larger comet that broke apart thousands of years ago. The debris from that ancient breakup is spread along a vast region of space, and Earth's orbit intersects it. Most years, the Taurids produce only a modest meteor shower, with 5 to 10 meteors per hour, but they are known for their fireballs, bright meteors that can be quite spectacular. The larger particles in the stream create these brilliant displays, and they hint at the presence of even larger objects. Some astronomers believe the Taurid stream contains asteroids tens or even hundreds of meters across, objects large enough to survive atmospheric entry and cause significant damage if they struck Earth. These objects are difficult to detect because they are dark and do not reflect much sunlight, but they are there, hidden in the stream, waiting for a close encounter. Evidence for these larger objects comes from several sources. Historical records describe exceptionally bright fireballs associated with the Taurids. Craters on Earth and the Moon align with the Taurid stream's orbit, suggesting past impacts, and telescopic surveys have detected a few asteroids moving in orbits consistent with Taurid membership. The Taurid complex is a reminder that meteor showers are not always harmless. While the dust and pebbles pose no threat, larger objects can and do reach the ground. Monitoring the Taurid stream, and other streams like it, is an important part of planetary defense, the effort to identify and track objects that might threaten Earth, near-Earth objects, and the impact threat. Meteors are the visible reminder of a larger truth. Space is full of debris, and Earth is a target. Near-Earth objects, or NEOs, are asteroids and comets whose orbits bring them close to our planet. Most will never strike us, but some will, and throughout history, some have. The dinosaurs are the most famous victims of an impact, but they are not the only ones. Smaller impacts have occurred throughout human history, some recorded, others inferred from geological evidence. The Tunguska event in 1908 flattened hundreds of square kilometers of Siberian forest when a meteoroid exploded in the atmosphere. The Chelyabinsk meteor in 2013 injured more than 1,000 people. Impacts are not just ancient history, they are ongoing. The good news is that large impacts are rare, Objects capable of global catastrophe, those more than a kilometer across, strike Earth only every few 100,000 years. Smaller objects, which can cause regional devastation, arrive more frequently, but are still uncommon. Most of the time, we are safe. But safe is not the same as invulnerable. The risk, while small, is real. This is why astronomers now dedicate significant effort to finding and tracking NEOs. Surveys scan the sky nightly, searching for moving objects. When one is found, its orbit is calculated to determine whether it poses any threat to Earth. So far, no known asteroid is on a collision course with Earth for at least the next century. The orbits are well understood, and we know we are safe from the objects we have found. But there are likely many more objects we have not yet found, particularly smaller ones that are harder to detect. The search continues. If an object were found to be on a collision course, what could be done? This question has driven research into asteroid deflection techniques. The goal is not to destroy the asteroid, which would create many smaller fragments, but to gently change its orbit so that it misses Earth. Methods under consideration include kinetic impactors, which ram the asteroid to nudge it off course, and gravity tractors, which use a spacecraft's gravitational pull to slowly tug the asteroid into a new orbit. In 2022, NASA successfully tested a kinetic impactor in the DART mission, deliberately crashing a spacecraft into a small asteroid and altering its orbit. The test proved that deflection is possible, that we have the technology to protect ourselves if given enough warning. The universe is vast and full of hazards, but we are not helpless. Comets, the source of wonder. Behind many of the most beautiful meteor showers are comets, the icy wanderers of the solar system. Comets are remnants from the formation of the planets, chunks of ice and rock that never coalesced into larger bodies. They orbit the Sun in elongated paths, spending most of their time in the cold outer regions, before swooping in for brief visits near the inner planets. When a comet approaches the Sun, the ice begins to sublimate, turning directly from solid to gas without becoming liquid. This gas carries with it dust and debris, forming a glowing cloud around the comet's nucleus called a coma. The coma can be larger than Earth, a vast, tenuous envelope that shines by reflecting sunlight and by fluorescing under ultraviolet radiation. The solar wind, a stream of charged particles flowing from the Sun, pushes the gas and dust away from the comet, creating tails. Comets can have two types of tails, a dust tail and an ion tail. The dust tail is curved, composed of small solid particles that follow orbital paths. The ion tail is straight, made of ionized gas pushed directly away from the Sun by magnetic fields. These tails can stretch for millions of kilometers, making comets some of the largest objects in the solar system, even though the nucleus itself might be only a few kilometers across. When a bright comet appears in Earth's skies, it can be a spectacular sight, visible even from cities, hanging in the heavens for weeks or months. Comets have inspired awe and fear throughout history. Their sudden appearances, their strange tails, and their slow movement across the sky made them seem supernatural. Many cultures viewed them as omens, often negative. The arrival of a bright comet might predict war, plague, or the death of a king. The most famous comet is Halley's, which returns every 76 years. It has been recorded for more than 2,000 years, appearing in historical documents from cultures around the world. Each return has been witnessed by a new generation, each contributing to the comet's legend. The most recent appearance was in 1986, and the next will be in 2061. Halley's comet is the parent of two meteor showers, the Eta Aquarids and the Orionids, But it is not the only comet to leave behind streams of debris. Comet Swift-Tuttle creates the Perseids. Comet Tempel-Tuttle creates the Leonids. Almost every major meteor shower can be traced to a comet, a reminder that these icy visitors are not just beautiful in themselves, but leave behind gifts that continue long after they have departed. The life of a comet. Comets do not last forever. Each time they pass close to the sun, they lose material. Ice vaporizes, dust is blown away, and the nucleus shrinks. After many orbits, a comet can become depleted, its ice exhausted, its activity ceased. What remains is a dark, rocky core, essentially an asteroid. Some comets die more dramatically. They can collide with the sun, vaporizing completely. Others break apart, fragmenting into multiple pieces that continue to orbit separately. Comet Shoemaker-Levy 9 famously broke into more than 20 fragments before colliding with Jupiter in 1994, creating impacts visible from Earth. The debris streams that create meteor showers are part of this long, slow death. Each time Earth crosses a stream, we sweep up particles that were shed perhaps centuries or millennia ago. The stream gradually disperses, spreading out along the orbit. Eventually, it becomes so diffuse that the shower weakens and fades. But new comets are always arriving. The Oort cloud, a vast spherical shell of icy objects surrounding the solar system, contains trillions of potential comets. Occasionally, gravitational disturbances send one of these objects falling toward the inner solar system. It might make a single dramatic pass, never to return, or it might be captured into a repeating orbit by the gravity of the planets. Long-period comets, those with orbital periods of hundreds or thousands of years, are constantly arriving from the Oort cloud. When they do, they are pristine, filled with ice and volatile materials that have been frozen since the solar system's formation. Studying such comets provides insights into the conditions and chemistry of the primordial solar nebula. Short-period comets, like Halley or Encke, have been around for many orbits and are more evolved. They have lost significant material and are approaching the end of their active lives. But they still put on shows when they return, and they still contribute to the meteor streams that grace our skies. Asteroids, the rocky cousins. While comets are icy, asteroids are rocky or metallic. They are the leftover building blocks of planets, chunks that never manage to assemble into a larger world. Most orbit in the asteroid belt between Mars and Jupiter, but some have orbits that bring them near Earth, and these are the ones that can create sporadic meteors and potentially pose impact threats. Asteroids come in a wide range of sizes, from boulders a few meters across to Ceres, which is nearly 1,000 kilometers in diameter and large enough to be classified as a dwarf planet. Most are irregular in shape, battered by billions of years of collisions. Their surfaces are often cratered, dusty, and ancient, preserving a record of the solar system's violent past. Some asteroids are solid chunks of rock or metal. Others are rubble piles, loose collections of fragments held together by gravity. These rubble pile asteroids are thought to be the remnants of larger bodies that were shattered by collisions. They are difficult to deflect because they absorb impacts rather than responding to them as solid objects would. Asteroids are classified by composition. C-type asteroids are carbonaceous, dark, and rich in organic compounds. S-type asteroids are silicaceous, made of silicate minerals and metals. M-type asteroids are metallic, composed primarily of iron and nickel. Each type tells a story about where in the solar system it formed and what materials were available at that location. When pieces of asteroids reach Earth as meteorites, we can study them directly. Iron meteorites, with their distinctive crystalline structures, come from the cores of differentiated asteroids that were once large enough to melt and separate into layers. Stony meteorites come from the outer layers of asteroids or from bodies that never melted. Each sample is a piece of a destroyed world. The asteroid belt is not the chaotic, crowded place often depicted in science fiction. In reality, the asteroids are widely spaced, with vast distances between them. You could travel through the belt and likely never see one with the naked eye. But there are many of them, perhaps more than 1 million, larger than a kilometre, and countless smaller ones. Occasionally, collisions in the asteroid belt send fragments spiraling inward toward the Sun. Some of these fragments cross Earth's orbit, becoming NEOs. Over time, their orbits may bring them close to Earth, and eventually, they might intersect our planet. When they do, they become meteors, the fiery endings of objects that may have wandered the solar system for billions of years. Interstellar visitors. In recent years, astronomers have detected objects passing through the solar system that did not originate here. These interstellar visitors are fragments from other star systems, wanderers that have crossed the vast distances between stars to briefly visit our neighborhood before continuing on their journeys. The first confirmed interstellar object was Oumuamua, detected in 2017. Its trajectory was hyperbolic, meaning it was moving too fast to be bound to the Sun. It had come from outside and would leave again, never to return. Its shape was unusual, elongated and tumbling, unlike most solar system objects. Its composition remains debated, with some suggesting it was a rocky asteroid, others proposing it was an icy comet, or even something more exotic. The second confirmed interstellar object was Comet Borisov, detected in 2019. Unlike Oumuamua, Borisov was clearly a comet with a coma and tail. Observations revealed its composition was similar to comets from our own solar system, suggesting that comet formation processes might be universal. These discoveries revolutionized our understanding of interstellar space. It is not empty, but filled with wandering objects, cast out from their home systems by gravitational interactions or explosive events. Some estimates suggest trillions of such objects pass through the inner solar system every year, though most are too small or too faint to detect. Could any of these interstellar visitors reach Earth and become meteors? Almost certainly, though distinguishing an interstellar meteor from a solar system, one, is nearly impossible. The entry speed might provide a clue, as interstellar objects could arrive faster than typical solar system debris. But detecting and studying such events requires luck and careful observation. The possibility that some meteors are interstellar adds another layer of wonder to falling stars. Each streak could be a piece of our own solar system, a fragment shed by a nearby comet, or it could be a traveler from impossibly far away, a grain of dust from a system orbiting another star, carrying the chemistry and history of an alien world. The pale blue trail. From space, Earth itself leaves a trail, not of light, but of particles. Our atmosphere is constantly being stripped away by the solar wind and by interactions with incoming meteors. Atoms and molecules from the upper atmosphere are energized and escape into space, creating a faint tail that extends behind Earth as we move through the solar system. This tail is invisible to the eye, but detectable by instruments. It is made of hydrogen and oxygen, the components of water, blown away from the top of the atmosphere. The process is slow, but over billions of years, Earth has lost a significant portion of its original atmosphere to space. When meteors enter the atmosphere, they contribute to this loss. The energy they deposit heats the upper atmosphere, giving some atoms enough speed to escape. In a sense, falling stars are part of an exchange. They bring material to Earth, adding dust and meteorites, but they also carry away bits of our atmosphere in their wake. This exchange is subtle, but it connects Earth to the wider cosmos in a tangible way. We are not sealed off, not isolated. We are part of the solar system, participating in flows of matter and energy that bind all the planets together. Every breath we take contains atoms that might once have been in space, brought here by meteors. Every breath we exhale sends atoms upward, some of which might eventually escape. The perspective from space also changes how we see meteors. Astronauts aboard the International Space Station have photographed meteors from above, looking down at the streaks of light appearing in the atmosphere below. From this vantage, meteors are not overhead but underfoot, glowing lines drawn across the dark face of Earth. Some meteors are bright enough to be seen from space even during daylight. Fireballs can outshine the sunlit atmosphere, creating brilliant flashes visible to astronauts. These events are captured on cameras aboard the station and shared widely, offering perspectives on meteors that no human had seen until the space age. Observing meteors, a guide. For those who wish to watch falling stars, the experience is simple but requires some preparation. First, find a dark location away from city lights. Light pollution washes out all but the brightest meteors, so the darker the sky, the more you will see. Second, allow your eyes to adjust. It takes at least 20 minutes for your eyes to become fully dark adapted. Avoid looking at phones or flashlights, as even brief exposure to bright light can reset the adaptation process. Third, lie down or recline in a comfortable position. You will be looking up for extended periods, and keeping your neck craned is tiring. A reclining chair, a sleeping bag on the ground, or a blanket spread on a hillside all work well. Comfort is important because the longer you watch, the more meteors you will see. Fourth, be patient. Meteors are unpredictable. You might see several in quick succession, then none for 10 minutes. The randomness is part of the experience. Use the quiet moments to study the stars, to let your mind wander, to simply be present under the night sky. Fifth, dress warmly. Even summer nights can be cool, and you will be sitting still for extended periods. Bring extra layers, blankets, and warm drinks. Being cold is the quickest way to cut an observing session short. If you are observing a meteor shower, aim to watch during the hours after midnight. Earth's rotation carries you into the direction of our orbital motion, increasing the relative speed of meteors and the rate at which they arrive. The radiant will be higher in the sky, making meteors more visible. No equipment is needed. Telescopes and binoculars are worse than useless for meteors, as they restrict your field of view. The best tool is your own eyes, wide open, taking in as much sky as possible. Some observers bring notebooks to record the meteors they see, noting time, brightness, color, and direction. Others prefer to simply watch, letting the experience unfold without documentation. Group observing can be enjoyable. Bring friends or family, spread out blankets, and watch together. When someone sees a meteor, they can point or call out, sharing the moment. The social aspect can enhance the experience, creating shared memories and sparking conversations about the cosmos. But solitary observing has its own rewards. Alone under the stars, with nothing but the darkness and the occasional streak of light, you can feel a deep connection to the universe. The silence, broken only by the rustle of wind or the distant call of an animal, becomes meditative. Time loses its urgency. There is only the sky, the earth beneath you, and the falling stars above. The stillness between meteors. The spaces between meteors are as important as the meteors themselves. In those minutes of waiting, of watching, the sky reveals itself in ways it cannot when you are rushing or distracted. You notice the subtle glow of the Milky Way. You see satellites drift by, steady points of light moving against the fixed stars. You catch the flicker of a distant airplane, its lights blinking. You might see a planet, bright and steady, holding its position, while the stars wheel slowly around it. You might notice the moon rising, its light gradually brightening the landscape and drowning out the fainter stars. You become aware of the Earth's rotation, the slow turning that makes the heavens appear to move. In the stillness, thoughts arise and drift away. Worries that seemed urgent during the day lose their grip. The perspective shifts. Seen from beneath the stars, human concerns seem small, temporary, not unimportant, but contextualized, placed within a larger frame. This is one of the gifts of meteor watching. It forces you to slow down, to be patient, to accept that you cannot control when the next meteor will appear. You can only wait, and in waiting, you practice presence. You learn to be still, to observe without demanding, to receive what the universe offers without grasping. When a meteor does appear, it breaks the stillness perfectly. A sudden flash, a streak of light, and then it is gone. The darkness returns, deeper than before. And you wait again, knowing another will come eventually, content to let the night unfold at its own pace. This rhythm, the alternation between meteor and stillness, mirrors larger rhythms in life: action and rest, event and interval, stimulus and silence. Watching meteors teaches these rhythms, reminds you that both are necessary, both have value. Meteor observing as meditation. Many observers describe meteor watching as meditative. The experience shares qualities with formal meditation practices: sustained attention, acceptance of what arises, non-judgment, presence. You sit or lie in stillness, focusing on a broad field of awareness, the entire sky. Thoughts come and go, like meteors, appearing briefly before fading. Unlike many modern activities, meteor watching cannot be rushed. You cannot make meteors appear. You cannot skip ahead. You must simply be there, open and attentive, allowing the experience to unfold. This enforced slowness is rare in contemporary life, and it can feel unusual, even uncomfortable at first. But as you settle in, as your eyes adjust and your mind quiets, the discomfort fades. You find a rhythm, your breathing slows, matching the stillness of the night. Your awareness expands, taking in more of the sky, more of the darkness. You become less focused on seeing meteors and more absorbed in the act of watching itself. When a meteor appears, you note it without clinging to it. It was beautiful, yes, but it is already gone. Trying to hold on to the image, to relive the moment, is futile. Better to simply acknowledge it and return to open awareness, ready for the next one. This practice of letting go, of being with impermanence, is central to many meditation traditions. Meteors are perfect teachers for this. They arrive without warning, shine brilliantly, and vanish completely. They cannot be grasped or possessed. They can only be witnessed and then released. Over time, regular meteor watching can cultivate qualities that extend beyond the observing sessions: patience, stillness, appreciation for fleeting beauty, a sense of connection to something larger than oneself. These are the deeper gifts of falling stars, the lessons written in light across the darkness, the science of meteor observing. While many watch meteors for pleasure, others contribute to scientific research. Meteor observing networks coordinate observers around the world, collecting data on shower rates, sporadic meteors, and unusual events. This citizen science helps astronomers track the behavior of meteor streams, identify new showers, and improve models of the solar system's debris environment. Observers report the meteors they see, noting time, brightness, color, speed, and whether they left persistent trains. This data, aggregated across many observers, reveals patterns that would be invisible to any single person. Shower rates can be calculated, peak times refined, and outbursts predicted. Some observers use video cameras to continuously record the sky. These all-sky cameras capture every meteor that appears above a certain brightness threshold. The footage is later analyzed, either manually or using automated software, to extract meteor information. Networks of such cameras can triangulate meteor trajectories, determining precisely where in the atmosphere they occurred and what their pre-entry orbits were. This trajectory data is valuable for understanding where meteors come from. By working backward from the observed path through the atmosphere, astronomers can calculate the meteoroid's orbit around the Sun before it encountered Earth. This reveals whether it was part of a known stream or if it might represent a new or unusual source. Radio observations add another layer. Meteors create ionized trails that reflect radio waves. By transmitting a radio signal and listening for reflections, observers can detect meteors even during daylight or through clouds. Radio meteor observing has revealed that daytime showers exist, streams that are invisible to optical observers because they occur while the sun is up. The combination of optical, video, and radio observations creates a comprehensive picture of meteor activity. This data feeds into models that predict future showers, assess impact risks, and improve our understanding of comets and asteroids. What began as simple wonder at falling stars has become a global scientific effort. Meteorites and what they teach us. The few fragments that survive to reach the ground carry extraordinary information. Meteorites are older than Earth, dating to the solar system's formation more than 4.5 billion years ago. They have not been altered by the geological processes that have reworked Earth's surface repeatedly. They are pristine samples, frozen records of ancient times. Chondrites, the most common type of stony meteorite, contain chondrules, small spheres of once molten rock. These chondrules formed in the early solar nebula, the cloud of gas and dust from which the sun and planets condensed. How they formed is still debated, but their presence shows that the early solar system was hot and dynamic, with regions of intense heating. Carbonaceous chondrites are particularly interesting because they contain organic compounds, including amino acids. These are the building blocks of proteins, essential to life as we know it. The discovery of amino acids in meteorites proved that organic chemistry occurs naturally in space, and it raised the possibility that life's ingredients were delivered to early Earth by impacts. Some meteorites contain water-bearing minerals, showing that water existed in the early solar system. Others contain tiny grains that predate the sun, formed in the atmospheres of stars that died before our solar system existed. These pre-solar grains are literally stardust, material older than our world, and studying them reveals the chemistry of previous generations of stars. Iron meteorites tell different stories. They come from the cores of asteroids that melted and differentiated, separating into metal cores and rocky mantles, just like Earth. When these asteroids were later shattered by collisions, their cores were exposed. Iron meteorites are fragments of those cores, samples of the interiors of worlds that no longer exist. The Widmanstätten patterns found in iron meteorites are particularly striking. When polished and etched with acid, iron meteorites reveal interlocking crystal structures that form beautiful geometric designs. These patterns form only during extremely slow cooling over millions of years, conditions that could only occur in the interior of a large body. They are visual proof of the meteorite's extraterrestrial origin. Lunar and Martian meteorites. Among the rarest and most valuable meteorites are those that come from the Moon and Mars. How do we know they come from these worlds? The chemistry matches samples returned by missions. Lunar meteorites have compositions identical to moon rocks brought back by Apollo. Martian meteorites contain gases trapped in their structure that match the atmosphere of Mars as measured by landers. These meteorites were blasted off their parent worlds by powerful impacts. When a large asteroid or comet strikes a planetary surface, the explosion excavates material and hurls some of it into space. Most fragments fall back, but a few achieve escape velocity and enter orbit around the Sun. Over time, gravitational interactions can send these fragments on paths that intersect Earth. Lunar meteorites are less rare, relatively speaking. The Moon is close, and many impacts over billions of years have sent material our way. Martian meteorites are rarer. Mars is farther, and the gravity well is deeper, making it harder for fragments to escape. Only a few hundred Martian meteorites have been found, compared to thousands of lunar ones. Studying these meteorites provides information about worlds we have barely begun to explore. Martian meteorites, for example, have revealed details about Mars's volcanic history, its atmosphere, and even the possibility of past water. One Martian meteorite, ALH 84001, sparked controversy when researchers claimed to have found fossils of ancient bacteria within it. While that claim remains debated, it highlighted the potential for meteorites to carry biological material. The idea that rocks can travel between planets raises intriguing possibilities. Could life, if it existed on Mars, have been carried to Earth by meteorite? Or could Earth life have been transported to Mars? This concept, called panspermia, suggests that life might spread throughout the solar system, or even beyond, carried by natural processes. Whether or not panspermia occurs, the existence of lunar and Martian meteorites proves that planets are not isolated. They exchange material, and by extension, they might exchange information. Each falling star could be a message from another world, a fragment of another planet's story arriving to tell its tale. The poetry of transience. Falling stars are symbols of impermanence. They remind us that nothing lasts forever, not even stars. Though we call them falling stars, and though we know they are not truly stars, the metaphor holds. Even real stars, those distant suns burning for billions of years, eventually die. Everything in the universe is temporary, existing for a time before transforming into something else. This is both sobering and liberating. If everything is temporary, then nothing need be grasped too tightly. Moments of beauty, like a meteor streaking overhead, can be appreciated fully precisely because they do not last. Their brevity intensifies their impact. We pay attention because we know the moment will not return. Poets and writers have long used falling stars as symbols. A falling star represents wishes, hopes, fleeting glimpses of beauty, or the passage of time. It can symbolize a soul departing, a dream fading, or an opportunity lost. But it can also represent wonder, magic, the unexpected gift of beauty in darkness. The Japanese concept of mono no aware, the awareness of impermanence and the bittersweet beauty it creates, applies perfectly to falling stars. There is sadness in their brevity, yes, but that sadness deepens the appreciation. We treasure them precisely because they cannot be held. In literature, falling stars often appear at pivotal moments. A character makes a wish on a shooting star, and the plot turns. Lovers watch meteors together, their relationship illuminated by the shared wonder. A lone traveler sees a fireball and takes it as a sign. These literary uses tap into something deep, the human sense that meteors are meaningful, that they carry significance beyond their physics. Even in our scientific age, this sense persists. We know what meteors are, yet we still feel that watching them matters. We still pause our conversations when one appears. We still point them out to our companions, sharing the moment. Knowledge has not diminished the wonder. If anything, understanding makes them more remarkable. Meteor showers and human connection. Meteor showers have become cultural events, moments when people around the world look up simultaneously. Social media fills with reports. Did you see that one? Amazing fireball just now. The Perseids are incredible tonight. These shared experiences create a sense of global connection. People separated by continents, united by the same celestial display. Astronomy clubs and planetariums often organize meteor watching parties during major showers. Families gather in parks or observatories, spreading blankets and setting up chairs. Astronomers provide context, explaining the shower's origin and pointing out constellations. Children stay up late, excited to see their first shooting star. Adults rediscover the wonder they felt as children. These gatherings create memories that last long after the meteors have faded. A child who sees the Perseids with their parents might remember that night for decades. A couple who watches meteors together on their first date might return every year, making it a tradition. Shared wonder becomes shared story, and the meteors become part of personal history. In this way, falling stars connect us not only to the cosmos, but to each other. They give us something to gather around, a reason to be together under the open sky. In an age when so much of life occurs indoors, mediated by screens, meteor watching offers something different. It is direct, unfiltered experience of the natural world. The accessibility of meteor watching is part of its appeal. You do not need expensive equipment or specialized knowledge. You do not need to travel to exotic locations, though dark skies help. You simply need to look up. This democratic quality means anyone can participate, regardless of background or resources. Falling stars in art and music. Artists have long been inspired by meteors. Paintings depicting falling stars often emphasize their dramatic contrast, bright streaks cutting across dark skies. The meteor becomes a focal point, drawing the eye and suggesting movement, energy, excitement. In music, falling stars appear in lyrics and titles. They represent wishes, dreams, fleeting moments of clarity or hope. Songs use them metaphorically, drawing on the cultural associations while adding personal interpretations. The image is flexible enough to carry many meanings, yet specific enough to evoke immediate recognition. Film and television use falling stars as plot devices or atmospheric elements. A meteor shower might provide a romantic backdrop for a proposal. A fireball might signal the beginning of an alien invasion or a supernatural event. Even when meteors are not central to the story, their presence adds wonder and unpredictability. The visual appeal of meteors has made them popular in photography and time-lapse videos. Images showing dozens of meteor trails converging on a radiant create striking compositions. Time-lapses that condense hours of observation into seconds show meteors raining across the heavens, their paths crossing and weaving, creating patterns that suggest choreography. Modern digital art has embraced meteor imagery as well. Animated wallpapers feature falling stars against cosmic backgrounds. Video games include meteor showers as environmental effects or gameplay elements. The aesthetic has permeated visual culture, becoming shorthand for mystery, magic, and the vastness of space. This widespread use in art and media reinforces the cultural significance of falling stars. They are not just scientific phenomena, but symbols embedded in our collective imagination. They mean something beyond their physical reality, carrying emotional and narrative weight that pure analysis cannot capture. The future of meteor science. Meteor science continues to evolve. New technologies enable observations that were impossible just decades ago. High-speed cameras can capture meteors in extreme detail, revealing structures and behaviors invisible to the human eye. Spectrographs can analyze the light from meteors, determining their chemical composition in real time. Networks of automated cameras now cover large regions, capturing every meteor above a certain brightness. The data is processed by computers, extracting trajectories and calculating orbits. This automation has dramatically increased the number of meteors tracked, providing statistical samples that improve our understanding of the meteoroid environment. Space-based observations add another perspective. Sensors on satellites can detect meteors from above, observing the infrared glow and the chemical signatures invisible from the ground. Some satellites are specifically designed to monitor meteor activity, providing global coverage and catching events that would otherwise go unnoticed. Looking forward, proposed missions might visit comet debris streams directly, flying spacecraft through them to sample the particles before they enter Earth's atmosphere. Such missions would reveal the unaltered composition of meteoroids, free from the chemical changes caused by atmospheric heating. Other proposals suggest using LiDAR, laser-based ranging systems, to study meteors. By bouncing laser pulses off the ionized trails, researchers could measure density, altitude, and other properties with precision. This technique could complement existing methods, providing new types of data. The ultimate goal is a comprehensive understanding of the meteoroid environment. How many objects are there? What are their sizes, compositions, and orbits? How does the population change over time? Answering these questions will improve impact risk assessments, aid spacecraft design, and deepen our understanding of the solar system's structure and evolution. But beyond the practical applications, meteor science serves another purpose. It satisfies curiosity. Humans want to understand the universe, to know how things work, to discover the principles underlying what we observe. Meteors, though small and fleeting, are part of that universe. Studying them is part of the larger project of understanding everything, the experience of a fireball. Those who have witnessed a true fireball often describe it as life-changing. The brightness, the size, the unexpected nature of the event combine to create an experience that feels significant, even transformative. Time seems to slow. The world is bathed in light, and then it is over, leaving only the memory and the afterimage. Some describe feeling awe, a sense of the sublime. The scale and power of the event overwhelm the ordinary. For a few seconds, the universe intrudes dramatically into everyday life, impossible to ignore. The experience can spark a lasting interest in astronomy, or simply leave a permanent impression, a memory that returns unbidden years later. Others describe feeling small, humbled by the display. A fireball is a reminder of forces beyond human control, of the vast machinery of the cosmos operating indifferently to our presence. Yet there is also beauty in this. The universe puts on a show, and we are here to witness it. There is often a social dimension. Fireballs are bright enough that multiple people see them simultaneously, even those not specifically watching the sky. Afterward, there is a flurry of communication. Did you see that? What was it? Was it a meteor? The shared experience creates instant connection among strangers, a moment of collective wonder. Fireball witnesses often report a desire to learn more. What was it made of? Where did it come from? Did anything reach the ground? This curiosity drives some to contact scientists, to file reports, to search for fragments. The event becomes a gateway, an entry point into deeper engagement with astronomy and planetary science. For scientists, fireball reports are valuable. They help track large meteoroids and identify potential impact sites. When fragments are recovered and linked to a documented fireball, the result is a meteorite with a known trajectory and orbit, a rare and precious dataset. Citizen reports make this possible, turning casual observers into contributors to science. Meteorite hunting adventures. Searching for meteorites is a blend of science, detective work, and adventure. When a fireball is witnessed and calculated trajectories suggest fragments might have reached the ground, teams mobilize. They travel to the predicted fall area, often remote and challenging terrain, and begin systematic searches. Finding meteorites requires patience and a trained eye. In rocky deserts, distinguishing a dark, fusion-crusted meteorite from similar-looking terrestrial rocks is difficult. In fields or forests, the task is even harder. Searchers walk in grids, scanning the ground, picking up anything suspicious. Most rocks turn out to be terrestrial, but occasionally, someone finds the real thing. The moment of discovery is electric. Holding a fresh meteorite, one that fell recently and has not been weathered, is to hold a piece of space. The fusion crust might still be shiny, the interior unaltered. Tests confirm what the finder suspects. This rock is not from here. Antarctic meteorite hunting is particularly productive. The ice sheets concentrate meteorites, and the white background makes them easy to spot. Teams travel to blue ice fields, regions where ancient ice is exposed at the surface. Over time, meteorites that fell elsewhere are transported by ice flow to these areas, creating natural collections. Thousands of meteorites have been recovered from Antarctica, representing a wide variety of types. The cold, dry conditions preserve them well, preventing the weathering that degrades meteorites in other climates. Some Antarctic meteorites are so well preserved that they could be mistaken for rocks from Earth's surface, except for their extraterrestrial chemistry. Desert regions, particularly hot deserts with little vegetation, are also productive. The Sahara, the deserts of Australia, and the dry valleys of Chile have all yielded significant meteorite finds. Local people sometimes recognize meteorites and bring them to scientists or sell them in markets. This informal network has contributed many important samples. The economics of meteorites. Meteorites have value beyond science. Collectors pay significant sums for specimens, especially rare types or those with interesting stories. A piece of a witnessed fall, with documentation and provenance, commands premium prices. Lunar and Martian meteorites are especially sought after, sometimes selling for thousands of dollars per gram. This market has created a community of professional meteorite hunters and dealers. Some individuals make their living finding and selling meteorites, traveling the world in search of fresh falls or productive hunting grounds. The business is competitive and sometimes secretive, with valuable locations guarded closely. The commercialization of meteorites raises ethical questions. Should these scientific samples be privately owned, or should they be preserved in museums and institutions for research and education? Opinions vary. Some argue that allowing trade creates incentives for discovery and brings meteorites to public attention. Others worry that valuable samples end up in private collections, inaccessible to scientists. Laws governing meteorite ownership vary by country. In the United States, meteorites found on private land belong to the landowner. Those found on public land are regulated differently depending on jurisdiction. Some countries claim all meteorites as state property. Others have no specific laws, leaving ownership ambiguous. Despite these complications, the market persists. Online auctions, mineral shows, and specialty dealers connect sellers with buyers. Museums acquire pieces for education and research. Private collectors build impressive collections, some of which are eventually donated to institutions. For scientists, the meteorite market is a mixed blessing. It provides access to samples that might otherwise never be found. But it also means competing with collectors for limited specimens and sometimes paying significant prices for research material. Balancing scientific access with market forces remains an ongoing challenge. Children and falling stars. Falling stars hold special magic for children. The experience of seeing a meteor for the first time is often memorable, sparking wonder and curiosity. Children ask questions. What was that? Where did it go? Can we find it? These questions are opportunities for learning, for introducing concepts about space, planets, and the solar system. Parents who take children outside to watch meteor showers create lasting memories. The experience teaches patience as children learn to wait for the next meteor. It teaches observation as they scan the sky attentively. And it teaches wonder as they experience the beauty and unpredictability of nature. Many scientists trace their interest in astronomy to childhood experiences watching meteors. Something about that first falling star ignited curiosity that never faded. The moment became a turning point, the beginning of a lifelong passion for understanding the cosmos. Schools sometimes organize meteor watching events as part of science education. Students learn about comets, orbits, and atmospheric phenomena. Then they put knowledge into practice, going outside to observe. The combination of theoretical learning and direct experience reinforces understanding and makes science tangible. Children's literature often features falling stars, using them as magical elements in stories. A character wishes on a falling star, and the wish comes true. A star falls to Earth and needs help returning home. These stories tap into the wonder children feel, wrapping scientific phenomena in narrative and imagination. As children grow, their understanding deepens. They learn the science behind the spectacle, the physics and chemistry of meteors. But the wonder often remains, now informed by knowledge rather than replaced by it. The falling star becomes more remarkable, not less, when understood as a fragment of a comet burning in the atmosphere. The therapeutic power of meteor watching. Beyond scientific interest and aesthetic appreciation, meteor watching offers therapeutic benefits. The act of lying under the stars, breathing deeply, and watching for meteors can reduce stress and promote relaxation. The darkness, the quiet, and the slow pace create conditions conducive to mental rest. Therapists sometimes recommend stargazing as a mindfulness practice, focusing attention on the sky, being present in the moment, and accepting whatever appears are all elements of mindfulness meditation. Meteors add an element of surprise and delight, rewarding sustained attention with occasional flashes of beauty. The perspective shift that comes from watching meteors can also be therapeutic. Everyday concerns seem smaller when viewed against the backdrop of cosmic processes. The vastness of space and time puts personal worries in context. This does not make problems disappear, but it can make them feel more manageable. For those dealing with grief or loss, meteor watching can offer solace. The impermanence of meteors mirrors the impermanence of life. Watching them appear and vanish can be a meditation on letting go, on appreciating beauty while it lasts, and releasing it when it passes. Some find comfort in the constancy of meteor showers, annual events that return regardless of human circumstances. The solitude of meteor watching can also be healing. Time alone, away from noise and demands, allows for reflection and processing. The darkness feels protective rather than threatening. The stars provide company without intrusion, and the meteors, when they appear, offer moments of connection to something beyond the self. Of course, meteor watching is not a replacement for professional mental health care, but as a supplemental practice, it offers genuine benefits. It encourages time in nature, promotes mindfulness, and provides perspective. These are all elements of well-being, available to anyone willing to look up meteor showers around the world. Different cultures experience meteor showers at different times and with different intensities. The geography of observation matters. Showers with radiance in northern constellations are best seen from the northern hemisphere. Those with southern radiance favor observers below the equator, but some showers, like the Perseids, are positioned such that they can be enjoyed from most of the inhabited world. In the southern hemisphere, observers have access to showers that northern observers miss entirely. The Puppet-Velid complex in December produces meteors, visible primarily from southern latitudes. The Alpha Capricornids and southern Delta Aquarids in July and August are also better placed for southern observers. Each hemisphere has its own calendar of celestial events. Cultural responses to meteor showers vary. In some regions, they are celebrated as festivals, occasions for gathering and celebration. In others, they are noted, but not particularly emphasized. The integration of meteor showers into cultural calendars depends on how visible they are and what other events occur around the same time. Traditional ecological knowledge in some cultures includes awareness of meteor showers. Indigenous peoples who navigated by stars would naturally notice regular meteor activity and incorporate it into their understanding of the sky. While this knowledge is less emphasized than the movement of stars or planets, it is present, woven into the broader tapestry of celestial literacy. Modern globalization has created a shared meteor calendar. Online communities track showers and share observations across borders. Live streams allow people in one hemisphere to watch showers occurring in another. The internet has made Meteor observing a global activity, transcending geographic and cultural boundaries, fireballs, and the news cycle. When a particularly bright fireball occurs over a populated area, it often makes the news. Videos captured by dashboard cameras, security cameras, and smartphones quickly circulate on social media. News outlets pick up the story, often speculating about what the object was and whether fragments might have reached the ground. This media attention serves several purposes. It alerts scientists to the event, allowing them to begin trajectory calculations and potential meteorite searches. It educates the public about meteors and their frequency, and it satisfies curiosity, providing answers to the questions people ask when they see something unusual in the sky. However, media coverage can also spread misinformation. Bright meteors are sometimes misidentified as satellites falling from orbit, aircraft crashes, or even UFOs. Correcting these misconceptions requires timely communication from astronomers and science communicators. Providing accurate information before speculation solidifies into belief. The ubiquity of cameras has transformed fireball documentation. Events that would once have been witnessed by only a handful of people and poorly documented now have multiple video recordings from different angles. This allows for precise trajectory reconstruction and orbit determination, turning chance sightings into valuable scientific data. Citizen science initiatives encourage people to report fireball sightings. Organizations like the American Meteor Society maintain online forums where witnesses can describe what they saw. These reports are compiled and analyzed, contributing to databases that track global meteor activity. The power of crowdsourcing turns casual observers into valuable contributors. The relationship between meteor showers and climate. On much longer timescales, meteor impacts have influenced Earth's climate. Large impacts, like the one that created Chicxulub crater, can throw enormous amounts of dust into the stratosphere, blocking sunlight and causing global cooling. These impact winters can last years or decades, collapsing ecosystems and driving extinctions. Smaller impacts do not have such dramatic effects, but they still contribute. Over millions of years, the cumulative dust added by meteors might influence atmospheric chemistry and radiative balance. The effect is subtle, dwarfed by other factors like volcanic eruptions or changes in solar output, but it is there. Some researchers have suggested that periods of increased meteor activity, perhaps due to passing through dense regions of interplanetary dust, could correlate with climate anomalies in the geological record. This hypothesis remains speculative, difficult to prove or disprove, but it highlights the interconnectedness of Earth and the surrounding space. Conversely, Earth's climate might affect how we perceive meteor showers. Cloud cover, which varies with weather patterns, determines visibility. In regions with monsoons or regular rainy seasons, major showers might occur during times when the sky is typically obscured. This geographic and climatic variation influences which cultures have historically paid attention to particular showers. Global climate change is altering cloud patterns and atmospheric transparency. How this will affect meteor observing is unclear. More clouds might obscure more showers. But changes in atmospheric circulation might also create new opportunities, altering when and where skies are clear during key observing periods. Rare meteor phenomena. Beyond the common meteors, there are rare phenomena that only occasional observers witness. Electrophonic sounds, already mentioned, are one example. Another is the perception of meteor smoke trails, faint, persistent trains visible in daylight. These are extremely rare and require specific conditions: a very bright fireball, clear skies, and a fortuitous viewing angle. Some meteors exhibit terminal flares, sudden brightenings just before they extinguish. These flares might result from fragmentation or changes in the meteoroid's orientation, exposing fresh surface to the airstream. Terminal flares can make a faint meteor suddenly brilliant, creating a dramatic punctuation to its fall. Precessions are rare events where multiple meteors appear nearly simultaneously, often moving in parallel. These occur when Earth passes through a swarm of closely spaced meteoroids, perhaps fragments from a recent comet breakup. The most famous precession occurred in 1972, when a large meteoroid grazed Earth's atmosphere, producing a fireball visible across North America. It skipped back into space without burning up completely, an extraordinary near miss. Meteor storms, producing thousands of meteors per hour, are rare but unforgettable. The Leonid storms of 1833 and 1866 were so intense that observers compared them to snowfalls. The sky seemed filled with falling stars, overwhelming the senses. Such storms occur only when Earth passes through unusually dense clumps of debris, events that happen irregularly and are difficult to predict precisely. Bolides that produce meteorite falls are rare enough that most people never witness one, but when they do, the experience is extraordinary. The bright light, the sound, the knowledge that fragments have reached the ground nearby, all create a sense of urgency and excitement. Searchers mobilize quickly, and finding fresh meteorites becomes a race against weathering and other collectors. The sound of meteors. Most meteors are silent, their light arriving without accompanying sound, but larger meteors, particularly bolides, can produce sounds that arrive minutes after the visual display. These are sonic booms, shock waves created when the meteor moves through the atmosphere faster than the speed of sound. The delay between light and sound is telling. Light travels at 300,000 kilometers per second. Sound travels at only about 340 meters per second, roughly 1 million times slower. If a meteor occurs at 100 kilometers altitude, the sound will take several minutes to reach the ground. Observers see the flash, then wait, wondering if there will be sound. When the boom finally arrives, it confirms what they witnessed was real and significant. The character of the sound varies. Sometimes it is a sharp crack, like a gunshot. Other times it is a rumble, like distant thunder, rolling across the landscape. Very large bolides can produce multiple booms as different parts fragment and create their own shock waves. Windows rattle, alarms trigger, and people far from the visual sighting investigate the source of the noise. In addition to sonic booms, there are the mysterious electrophonic sounds that occur simultaneously with bright meteors. These hisses, clicks, and crackles remain not fully explained, though electromagnetic induction is the leading hypothesis. Not everyone hears them, and they seem more common among observers in open areas near conductive materials. Recording meteor sounds is challenging. Microphones can capture sonic booms, but the electrophonic sounds are subtle and easily missed. Researchers have deployed instrumentation to study these phenomena, but much remains unknown. Each fireball that produces sound offers a new opportunity to gather data and refine theories. Meteorites as historical records. Meteorites are not just geological samples, but historical documents. They record events from the solar system's past, preserving information that has been erased elsewhere. Some contain pre-solar grains, minerals that formed in previous stars and somehow survived the sun's formation. These grains are older than the solar system itself, tiny time capsules from an earlier epoch. Other meteorites contain inclusions rich in calcium and aluminum, the first solid materials to condense from the solar nebula. Dating these inclusions provides the age of the solar system, currently estimated at 4.567 billion years. This number, foundational to planetary science, comes from meteorites. The textures and structures within meteorites reveal processes that occurred during planet formation. Chondrules, those small spheres found in many stony meteorites, formed through rapid heating and cooling, likely from shock waves or lightning in the solar nebula. Their presence shows that the early solar system was dynamic, with energetic events shaping the material before planets formed. Metamorphism in some meteorites indicates they were heated and compressed, likely inside larger parent bodies. By studying the degree of metamorphism, scientists can infer the size and thermal history of these bodies. Some were large enough to have differentiated layers. Others remained small and cold, never reaching temperatures sufficient for melting. Impact features in meteorites, such as shock veins and melt pockets, record violent collisions. The solar system's early history was marked by intense bombardment, with impacts reshaping bodies repeatedly. Meteorites bear the scars of this violence, tiny witnesses to a chaotic past. By analyzing isotopes in meteorites, scientists can determine how long they traveled through space before reaching Earth. This cosmic ray exposure age reveals how long the fragment existed as a small object exposed to radiation. Short exposure ages suggest recent breakup of the parent body. Long ages indicate the fragment wandered for millions of years before encountering Earth. The future: more meteors or fewer? The rate of meteors reaching Earth is not constant over geological timescales. The solar system's debris environment changes as comets break apart, asteroids collide, and orbits evolve. Periods of increased activity might occur when Earth passes through particularly dense regions or when fresh comets enter the inner solar system. Some scientists speculate that major impacts, like the one that killed the dinosaurs, might be part of periodic cycles. If the solar system periodically passes through regions of the galaxy with higher comet densities, impact rates could vary over tens of millions of years. This hypothesis remains controversial, with evidence both supporting and contradicting it. On human timescales, meteor shower activity changes more subtly. Streams gradually disperse, reducing their density and the meteorites they produce. But new streams form as comets shed material, potentially creating new showers. Predicting these changes requires detailed modeling of orbital dynamics and comet behavior. Human activity might also affect meteor observations, if not the meteors themselves. Increasing light pollution makes it harder to see faint meteors, effectively reducing apparent shower rates, even if the actual rate remains constant. Efforts to preserve dark skies are partly motivated by the desire to keep meteor watching accessible to future generations. Space exploration might eventually alter the meteor environment. If large-scale mining of asteroids becomes feasible, the debris created could add to the background. Alternatively, technologies developed for deflecting hazardous asteroids might be used to clear particularly dense streams, reducing the risk to spacecraft. These possibilities remain speculative, but they illustrate how humanity might one day interact with the meteor environment deliberately. Meteors in space. For astronauts in orbit, meteors appear different than they do from the ground. The International Space Station orbits at about 400 kilometers altitude, roughly the same height where meteors become visible. Astronauts sometimes see meteors sideways, glowing trails appearing level with or below their position. This perspective is surreal. From the ground, we look up at meteors. From space, you might look down or across at them. The realization that you are at the edge of where meteors occur, that you are in the same environment they inhabit briefly, is humbling. It emphasizes how thin the boundary is between Earth's protective atmosphere and the vacuum beyond. Meteors also pose a risk to spacecraft. The same particles that create beautiful light shows on Earth can damage satellites, space stations, and vessels. At orbital velocities, even tiny particles carry significant energy. A grain of sand hitting a spacecraft at 10 kilometers per second impacts with the force of a bullet. Larger objects can be catastrophic. This is why spacecraft are designed with shielding and why the International Space Station has Whipple shields, layers of material that cause incoming particles to vaporize before reaching critical components. Meteor stream forecasts are part of mission planning, with spacewalks and sensitive operations sometimes scheduled to avoid periods of high activity. Observing meteors from space offers scientific opportunities. Instruments can be aimed to view meteors from the side, measuring properties difficult to assess from the ground. The lack of atmospheric distortion allows for clearer imaging, and continuous monitoring without day-night cycles enables comprehensive surveys of meteor activity. Future missions might even visit comets and asteroids, studying the parent bodies of meteors directly. Samples returned from such missions would be pristine meteoroids, never exposed to atmospheric heating. Comparing them to meteorites would reveal what is lost or changed during entry, improving our understanding of how material is altered as it becomes a falling star. The personal meaning of falling stars. Ultimately, the meaning of falling stars is personal. For some, they are purely scientific curiosities, interesting phenomena to study and understand. For others, they are aesthetic experiences, moments of beauty appreciated for their own sake. For still others, they carry spiritual or symbolic significance, representing connection to something larger. All these perspectives are valid. Falling stars are large enough, metaphorically speaking, to hold multiple meanings simultaneously. They can be understood chemically and physically, while also being appreciated as symbols of impermanence. Science and poetry are not mutually exclusive but complementary ways of engaging with the same reality. What matters is that falling stars continue to inspire. They call us outside, away from screens and artificial light, into direct contact with the night. They remind us that the universe is active, that things are always happening, that the cosmos is not a static backdrop, but a dynamic stage. Each person who sees a falling star adds their own story to the collective tapestry. The wish you made, the person you were with, the moment in your life when that particular meteor appeared. These personal meanings accumulate, creating a rich cultural phenomenon that transcends any single explanation. And so we continue to watch. Year after year, generation after generation, humans look up during meteor showers and sporadic falls, witnessing the same basic phenomenon that amazed our ancestors. The technology changes, the explanations evolve, but the essential experience remains. A sudden light in the darkness, brief and beautiful, reminding us of our place in an immense and wondrous universe. Closing reflections. As we come to the end of this journey through the world of falling stars, it is worth reflecting on what we have explored. We have traveled from the ancient mythologies that first tried to explain these mysterious lights, through the scientific revolution that revealed their true nature, to the modern understanding that sees them as messages from the cosmos, fragments of comets and asteroids burning briefly before our eyes. We have learned that falling stars are not stars at all, but grains of dust, pebbles of rock, occasionally large boulders, all moving through space until they intersect with Earth. We have discovered that they come from comets shedding material as they orbit the Sun, from asteroids colliding in the belt between Mars and Jupiter, from impacts on other worlds that eject fragments into space. We have seen how these tiny travelers, most no larger than a grain of sand, create spectacular displays as they plunge into the atmosphere at speeds that seem impossible. We have explored the meteor showers that grace our skies each year, reliable visitors that arrive on schedule as Earth passes through debris streams laid down centuries or millennia ago. We have stood in wonder before the great fireballs and bolides, those rare events when something larger arrives, bright enough to cast shadows, loud enough to rattle windows, spectacular enough to make the news and live in memory for years. We have learned about the even rarer meteorites, the fragments that survive to reach the ground, carrying with them secrets from the dawn of the solar system. We have traced the cultural history of falling stars, from omens and divine messages to objects of scientific study and sources of wonder. We have seen how different cultures have interpreted them, what stories they have told, what meanings they have found in these brief flashes of light. We have explored the practical aspects of meteor watching, the patience it requires, the dark skies it rewards, the simple joy of lying beneath the stars and waiting for the next streak to appear. We have discovered how this practice can be meditative, therapeutic, connective, creating shared experiences and personal memories. And through it all, we have touched on the deeper meanings that falling stars carry. Their impermanence reminds us that nothing lasts forever. Their beauty shows us that brief can be better than eternal. Their unpredictability teaches us to be present, to watch with open attention, to receive what comes without grasping. As you lie here now, letting these thoughts settle, imagine yourself beneath a dark sky. Picture the Milky Way arching overhead, that river of stars that is our galactic home. See the constellations wheeling slowly as Earth turns, the ancient patterns that have guided travelers for millennia. And then, as you watch, a meteor appears, a brilliant streak, cutting across your field of vision. Here and then gone, you make a wish, or perhaps you simply smile, appreciating the moment for what it is. Another meteor follows, and another, each one unique, each one a tiny fragment of cosmic history, making its final journey. The night is long, and you have nowhere to be. The meteors will continue to come, one by one, sometimes in clusters, sometimes with long pauses between. You watch, you drift, your mind growing quiet, your body relaxing into the darkness. The boundary between waking and sleeping grows soft. Meteors continue to flash, even as your eyes grow heavy. They are always there, always falling, always lighting up some part of Earth's atmosphere. The universe continues its ancient dance, indifferent to whether we watch or not, yet somehow more complete when witnessed. Let your breathing deepen. Let your thoughts drift like meteors across the dark sky of your mind, appearing and vanishing, leaving no trace. Feel yourself settling into rest, into sleep, into the vast quiet that holds all things. The falling stars will continue without you. Tomorrow night, if you wish, you can watch again. For now, let them carry you gently into dreams. Close your eyes and know that somewhere, above the clouds, above the atmosphere, in the silent reaches of space, fragments of ancient comets are falling toward Earth, ready to blaze brilliantly across tomorrow's darkness. Sleep now. Rest beneath the falling stars. Let their light guide you into peaceful slumber. Good night.